and gentlemen, we are Group 11, and this is our senior design project. This is my team, Daniel, Ryan, and myself, Charles English. Our project was the R.O.V.er, stands for Underwater Remotely Operated Vessel. Now, what a remotely operated vessel is a underwater vessel that's supposed to designed to perform different tasks and objectives. Now, our focus for our vessel was to have it tethered to the surface, which means there's a cable that connects communication and visuals to the surface, and it's non-autonomous, which means that there's an actual person controlling it. It doesn't go off by itself. Now, our design standards and restrictions, we went off of a mate competition, which we will be competing in June of 2015. Here are some companies and different universities across the world that have focused on underwater vessels. Most of these companies are located in America, Asia, and Europe. Now, for the mate competition, there are specific classes and guidelines that you have to follow. Our vessel falls in the Explorer class, and this year's Explorer class objectives were based really around ice, the Arctic setting, as well as repairing and maintaining pipelines. So our vessel must be able to go under sheets of ice, collect samples, place sensors, as well as go along streams of pipeline, view maintenance, and see if anything needs to be repaired. Now, for the main competition, we have specific guidelines that we have to follow. Specifically, size had to be no bigger than 75 by 75 centimeters area, as well as it has to be man-portable, easily maneuverable. We had to calculate the drag analysis. The material selection was very important. It needed to be sturdy, it does not corrode, and it needed to be able to expand hardware, as in being able to attach different components, maybe change out the gripper or add light fixtures and such, as well as software, be able to be controlled by different operating systems. Now, for our team personal goals, the mate requirements start for the testing at 25 to 30 feet. We as a team decided we tried to go far past that and operate this at 100 feet. We wanted to increase the thrust power to make it to overcome some currents, because in certain parts of in the ocean, current could be up to 6 meters per second and 6 miles an hour. Miles an hour, I apologize. And we wanted our vessel to overcome those currents, as well as use our Arduino controller to advance the controls of our system, and we wanted to reduce the cost, as well as operate on a regular car battery, D12. Now, as you see here are two very different types of vessels. To the left, you have a very simple open ROV kit. It's really cheap, designed to do 1 or 2 specific tasks. And you see on the right, there is a very, very complex, higher cost vessel designed to do multiple tasks. And it's now, we took these two designs and we contemplated a lot of different what we wanted to do or where we wanted to go with our design. And as you can see here, this is our final design. You see a rigid structure with reinforcement beams. We have 2 vertical thrusters to ascend and descend in the water. We have 2 horizontal thrusters to move forward and backwards, as well as pan. We have a gripper that we can control, and 2 clear PVC pipes. One to main the housing of most of our electronic systems, and then the front one so we can house sensors and cameras. Here's a quick dimensions of our vessel. The greatest dimension is 18.27 inches, which is about 2/3 of the requirement for the mate competition. So we're well within that range of that part of the standard.
Real quick, here's some of our standards. Primarily, we were concerned with the mate ROV competition rules. That requires shrouds surrounding the props for safety purposes. Also, no sharp edges. All the copper wiring on board must be sealed, so there can't be any exposed copper. One of the additional things that we have to still implement is doing 48 volt to 12 volt DC on board conversion of power. Additional to that, we had to go and design the sub, so we looked into other specifications, and one of the standards we thought would be relevant was the ascending pressure vessel, but it only applies to metal structures and at a higher pressure than what the ROV's going to be experiencing, so it didn't really apply to this project. And we had our standard hardware specifications from ASME and the AMS for the aluminum cross members. Real quick, here's a block diagram of our functional block diagram for our system. It shows basically topside where the operator is going to be, the workstation, which is going to receive signal from the Arduino microcontroller, relay that information back to the operator, and it's going to send the signal down to control the ESCs to go and give that translation of the controls on the surface to underwater. Being that this is moving through a body of fluid, we had to do drag analysis. As you can see, due to the drag analysis, velocity is essentially squared, which is going to cause an exponential increase. So we wanted to stay in the lower velocity ranges, and we decided 3 meters per second for our design criteria because that puts us slightly beyond the greatest ocean currents, and it's still somewhat lower in the resultant forces. With our drag simulations, we did hand calculations that Daniel conducted, and we also ran it on SolidWorks, and our results were both comparable, so we feel that they are valid results, and that we were able to proceed with designing the ROV based off of this information. For the pressure vessels, we did a pressure vessel analysis for a thick body cap structure with external pressure applied. From this, we were able to get a series of the stresses that compose all the loading. We applied the maximum shear stress theory to it and found the factor of safety. Those were plotted onto a table, which shows basically, with our calculations, at about 250 feet, we should have a minimum factor of safety of around, I believe it was 7. We ran the pressure stress simulation on SolidWorks as well. As you can see where we selected our fixtures and the loading that was going on. We decided to do it for 70 feet, just because that's where a lot of stuff gets critical for loading with our 100-foot range. At 70 feet, we found the factor of safety to be 10.12, so it's actually not as in line with the hand calculations. As we moved on from the analysis, we got into construction. We decided to use a skeletal-based frame using acrylic side panels and aluminum cross members. For the ducts, we used PVC ducts and PVC for the electronics housing. All these materials are recyclable after the end life of the ROV. Additionally, we had to rig the motors, which we used a 1000 kV brushless motor, primarily because it's a sealed coil, so it doesn't need any additional waterproofing for the system. We selected a 75mm prop just to get us enough power to be able to try to meet our design specifications for our speed. And we have that system powered by a 45 amp brushless CSC with reverse to allow us to be able to back this up if we get it into a tight corner.
In designing the control software for the ROV, we explored many options. We settled on MATLAB because it was an environment the entire group was comfortable with, as well as afforded several debugging tools that would make coding and troubleshooting the control software easier, much easier and more streamlined. So we had about 6 iterations of the control software. Initially, we started off with a keyboard control, very simple keyboard input. You press forward and enter, and the ROV would travel forward, so on and so forth for the other cardinal directions. It worked, but it wasn't very good. So I implemented analog gamepad input, used the analog game controller, and that's for the thruster as well as the gripper, and it made the control more intuitive and much easier. The current iteration of code is about 350 lines of code, and also added instantaneous temperature monitoring because the ESCs generate a bit of heat during operation. So in order to not exceed the operational temperature of the microcontroller, we wanted to monitor and log the operating temperature within the compartment. We noticed through our testing that we did not exceed more than about 110 degrees Fahrenheit. So having designed the control software and having actually built the ROV, we went forward with testing. So the primary test that we conducted. First and foremost, waterproofing. After waterproofing tests were completed, we went ahead and did buoyancy tests, tested maneuverability, speed, and grasping for performing tasks underwater. So here's a short video of the testing that we did on the ROV. So you see here is descending into the water. We designed the ROV to be neutrally buoyant, so that level is controlled by the vertical thrusters and not any other sort of buoyancy control. And here's grasping. So you can see the ROV can actually perform tasks underwater and grasp as necessary. So here's some of the testing results. Initial waterproof testing, we had slight leaks through the end pipes. They required a rubber sealant. We were not satisfied with how that came out, but with the rubber sealant, we were able to waterproof the caps and move forward. Buoyancy testing, initially the ROV came out slightly positively buoyant. We added weight so that it would become neutrally buoyant, so that way the thrusters would not have to fight that upward buoyancy force to control level in the water column. Additionally, we did speed test and found the speed to be approximately 1.5 meters per second. This is 50% less than expected, and we surmised that the possible causes of this reduction in speed is the torque rating on these brushless DC motors. Typically, they're used for applications such as quadcopters, and they operate in air. So operating in water, they're not as efficient. The higher torque requirement leads to a lower RPM output, as well as voltage drop across the tether. We have about a 3-volt drop across the tether, so it means the motors were operating at about 9 volts instead of the prescribed 12 volts. And this leads to an exponential reduction in the operation of the motors. In addition, during ascent and descent, we noticed rotation. I'm sure you noticed in the video of the ROV. And the cause of this is, if you look at the diagram on your left, the vertical thrusters spin in a uniform direction. And this causes an overall torque on the rover in the water. It causes a moment that causes rotation about the z-axis. So possible solutions in the future, we can manufacture a prop that will allow the motors to spin counter to each other while still producing thrust in the same direction. This will zero out the torque. Or we can use the horizontal thrusters to produce force coupled to zero out the torque. Future work, we need to install a 48 volt to 12 volt converter on board the ROV. This will satisfy the competition requirement as well as alleviate the issue of voltage drop across the tether. In addition to that, we need to install an improved camera. The visuals were not great. An improved camera will make the operation for the pilot much significantly more easy, and they will be able to perform tasks better. We need to incorporate additional sensors, accelerometer, and also as well as an orientation sensor. We'd like to improve the tether system. Right now it's one solid cord, it's not detachable. Obviously that's not ideal, so we need to make improvements to that. As well as porting the control code to other languages. As I touched on before, the control code is written in MATLAB. It's perfect for our applications. Being students, we have access to MATLAB, but if you do not have a MATLAB license, it can be costly to purchase one for use. So porting the control code to other languages will allow greater access to this platform. We also would like to install higher torque brushless motors to improve the operation underwater, as well as install accessories for additional environments and tasks, as you can see on the So some lessons learned. 3D printed end caps were unsuitable for the pressurized housings. It saved us some time in manufacturing, but it gave us headaches down the line in waterproofing. We had several leaks. So in the future, that can be improved by turning the end caps out of solid stock, and it's going to improve the quality of the end caps. The camera housing, you can see the camera housing is very opaque. We sourced the parts online, and really they were not as we expected. So the visuals are not very good outside through the camera housing. So we would like to, in the future, take more care in sourcing parts online. In addition, the initial designs required some slight modifications after manufacturing consultation in order to improve the ability to manufacture them. So in future designs, take that into account. It's something that's very easy to overlook, but keep that in mind when doing your initial designs. As well as the symmetric design of ROV simplified a lot of the analysis and construction of the vehicle. So here's a cost breakdown. This is our timesheet. Has the tasks and a breakdown for the group work, as well as the total time. We estimated about 121 man-hours of work for this project. Our materials cost sheet We projected a price initially of $651, and it came out to about $531. So less projected cost was slightly higher than what we ended up with. So our total cost, including materials, manufacturing, and development hours, is about $4,375, which is fairly high. But if you look at the materials and manufacturing, it's about $750. If you look at other ROVs on the market, open ROV, you can buy the kit for about $800. It's very slow moving, doesn't have a gripper. It's basically used for observations only, as well as the Sea Lion ROV is $4,500. So we feel that our prototype cost is in line with what we expected. Here's a timeline for the project. We followed it fairly closely. It allowed us to do testing and troubleshooting towards the end of the project. So something that we touched on earlier is this idea of having this as a platform for use beyond just the main competition. So we tried to design the ROV from the ground up to be easy to use, expandable. If you look at my control code, it's well documented. You can go in and change any kind of parameters to suit it to your needs. We have a lot of places on the ROV where you can mount hardware. You can trim the weight for specific buoyancy for whether it's saltwater or freshwater. So here's some of the applications of such device outside of the main competition. Here, this slide illustrates the goal that we had initially versus the reality, and we feel we closely achieved. Here's the references for our project. That concludes the presentation. We have a short video while we take questions. Thank you.
So this is just a quick timeline of the video. Dr. Levy?
For this competition, is this a saltwater competition or a freshwater
It's in
competition?
the pool.
It's in a
freshwater.
Yeah, it's a freshwater swimming pool.
Okay, so if you had to do, I mean, you're talking about doing this, or as far as the competition is concerned, doing work under the ice and things like that. What kind of changes would you have to make in order to handle saltwater competitions?
For saltwater, mostly it would just be trimming the buoyancy because of the added density of saltwater. With extended service in saltwater, some of the materials will have erosion occurring. So the aluminum will eventually oxidize if it isn't properly rinsed and taken care of to remove any mineral deposits. But aside from that, it should just be buoyancy adjustments.
What about cold?
The Arduino is actually specified to range from 50 degrees Celsius, I believe, to like 150 degrees. So it has a pretty good range of applications for temperature. So it should be fine for the cold weather.
Cold water? Under the water?
You said 50 or minus 50?
I believe it was 50 Fahrenheit to 150 Fahrenheit. I don't recall exactly, but I know that it.
That's not
That's
cold.
not very
I mean,
cold.
the ESCs are also putting off heat, and I mean, there are some adaptations that we can do. It's a simulated environment, so for like the actual competition, it's fine.
Yeah.
But for actually like using it for an Arctic exploration, we're probably gonna have to do some installation for the hardware and do some adjustments.
How long was your cord, your wire?
It's-
Your tether?
Yeah, the USB is 65 feet, the power cable is 100 feet, just so that way we can try to keep the power away from the pole a little bit.
Okay, so if you designed it for 100 feet,
Yeah.
okay, which would basically mean that your guy's got his hand inside the water as he's trying to move it around. It's approximately, 5 feet by 5 feet?
Well, that's just what we set up for testing, and due to having slightly cheaper costs, using the USB interface rather than Ethernet, it allows for easier serial communication through MATLAB. So it was just to kind of expedite our testing and to get us working a little bit easier.
But do you understand what I'm asking?
Yeah, we can always go and change the tether out, and that's,
And what would happen in terms of voltage drop when you do that?
with the voltage drop, if we go and run the 48 volts, we could actually run a smaller gauge cable. We'll have the voltage conversion going on board, so there really won't be any significant manner to it. It should be.
Typically, when you transfer power at a higher voltage and a lower current, you have less I-squared R losses. So transmitting the power at 48 volts, it's going to be a significantly lower current, and then we're going to be down converting it on board to 12 volts. So the voltage drop is going to be significantly less when we transmit at 48 volts instead of at 12 volts.
Can you go to a slide where you mentioned the goals?
Main objectives.
Our personal or the competition?
Any of them. Just what were your goals for the whole project, I guess?
Our goals were to be able to create the made ROV.
Primarily meet the competition requirements.
So do you guys feel like you did that?
Yes.
So you can go and compete in this competition right
With the
now?
exception of the 48 to 12 volt converter.
Okay. So again, just remind me, you have to go underwater, pick something up, come back out. What was the goal? I don't remember seeing it really anywhere.
The competition objectives are
Okay.
right here.
Could you make that big so we
Yeah.
can see it?
So what is the competition? What are you doing?
It's basically maneuverability underwater, being able to complete tasks in a timely manner, picking up objects, replacing objects, doing underwater surveying.
So you can deploy and recover sensors. You can locate and measure icebergs. You can.
I mean, several of these components are covered by visual feedback, the camera and the gripper.
So you can measure an iceberg with the camera that you have on there now?
Not the one that's on there right now.
Not as efficiently as we'd like, or not as good as we'd like.
So I guess my point to all of this is you lay out some stuff in the beginning, which again, I don't really know, it was very hard to see, right? I really don't know you did some stuff, and at the end, I really don't know if you met those goals or not, right? It's really hard to tell. And that's project management, right? So make sure that when you're running a project, at the end, if you can do it, let us know. I mean, it was hard to tell if you could or not. you know?
Yeah, primarily our main changes are that we have to do the 48 volt conversion and the camera, and then.
And you also had ceiling problems, right? You said you had ceiling problems?
Yeah, I mean,
So-
right now it's sealed up and working fine, but if we
Okay.
do any future work on it, we would like to try to replace the end caps.
Okay.
Yeah, did you have to follow some kind of a path as far as the competition is concerned? When you're talking about, conduct a closed visual inspection or move around, deploy or recover sensors, etc. Do they drop those things inside a pool, and then you have to go and follow some certain path to try and find these things? So
There's no like direct path, they just give you an objective and you have to figure out where it's at and what you have to do with each scenario.
Is there like some kind of timeline in the competition, like you need to go get that bottle of water right there, you have something ready to sit down, or?
There are time limits, and each.
So what are the
team is-
time limits? This all helps, right? Anyway, go ahead. Yeah.
I understand it helps, but it's a little bit young. So, like, we designed the ROV to go under. It might not win the competition, but it sure as heck is going to perform these tasks.
I get it, but if we don't know what the competition is, it's very hard for us to assess what you guys are doing, right? They're definitely, all these competitions have very, very specific rules, right? That's all I'm saying. It would be really great to know those and to see how well you guys can meet those. That's your objective, right? That's all I'm saying.
Okay, looking at task one, if that's what you're supposed to be doing, it talks about samples of algae and ice. Did you ever take into account that algae could get into those crops, and the next thing you know, I've got the whole thing wiped out?
Well, that's part of, with our future work, we have developing additional accessories. So,
Accessories could be anything.
That's one of the additional accessories that we considered for the competition, being that it's in a pool, there's no real chances of like debris entering that system.
I just like, I think of California with the big long outfit.
Yeah, no, I
You
mean,
get that in there, you're done.
with it being in a confined pool, there's no real chances of like debris entering it and damaging it, but that's one of the additional accessories we did consider.
Because you need to be pulling, or you're not going to be able to keep the gripper on the part that you're trying to go after.
Yeah,
So you'll be pulling that stuff right into those motors.
but that's additional stuff. I mean, the ducts are a standard 3-inch PVC, so you could go and get a cap in if you feel confident in choking the flow that much. You could essentially put like a screen mesh over it with a standard PVC cap and have it somewhat foolproof for that type of scenario. Being that the competition's in a pool and that's our primary objective, we neglected that portion of designing additional features for it.
Okay. The gripper itself, why is it a one direction or 1 degree freedom?
That's because with our duct layout, we were intending to get a pitching moment going, and the rotation about the Z-axis as well.
But you didn't get that, correct?
We didn't get to the point of implementing the pitching, but we have most of the.
Which would have been a programming event?
Yeah.
So are the motors basically in one direction? Can you run all of those motors at the same time?
Yes.
And have you done any work to see if there's any combinations that gets you levels of control that we didn't see?
In future work, we manufactured this thing from scratch. So, and I was developing the control software alongside. So, most of the time I was working on the control software, I didn't have a functioning ROV to test. So I was working with little servos, right, to make sure that my outputs were correct. I was using MATLAB. You can see your variables very clearly. So I was using MATLAB's debugging and tools that were associated with that. So it's kind of difficult to really program for something that's not built yet. So, but once we finally manufactured it and got it in the water, we did some more testing and tweaking, and I would like to do more.
Are you competing in the competition?
Yes, in June.
In June, and you'll be working on, I assume, all of that kind of feedback. Okay, thank you.
Now that you finally got it working and you did testing, did you find it to, stuff came up that you didn't expect? In other words, you figure it should go like this, but in reality it was going like this. You know?
Slightly, yes. There were some issues like that. Yes.
Because I'm wondering, while say you're going forward, then you could use the other motor, say it's going too high, you tweak it or you make it, try to keep it back in the same line.
That goes into as well, on this side, particularly the additional sensors, accelerometer and orientation. I don't currently have those sensors on the ROV, but with those sensors, I can have feedback.
Right.
So I can implement some sort of big control so that I can maintain orientation or direction using that feedback.
Yeah, and you thought about, this is my last question, as far as the camera ones, because the plastic is not so, have you thought of trying to buff it in a way where it makes it nice and clear? Because you can take plastic, you can sand on it real fine, and then with a polisher, you can polish it, and then it comes out like glass.
There's an actual like bluish hue to the plastic that I think it's gonna have distortion. Plus, it's essentially gonna end up being a convex lens, so it's gonna have distortion along that vertical line. So we kind of like to try to reassess the whole like forward tube
The source new part.
and
material.
find a way to like alleviate everything.
Right.
Its speed is pretty good actually. 1.5 meters is quite fast in water, but they need a good experience maneuverability. So you need to grab that Coke bottle faster. Okay, thank you very much.